So yeah, I'm Jon Hathaway. Sorry for the bit of the delay here, but we're rolling now, and I'm appreciative for the Forest Service for putting this on and letting us talk about some of the data we've collected over the past few years and the data that is kind of hot off the presses related to rainfall interception. And I see some people on the line doing similar research and some friends and colleagues on here. So thanks for joining, and we definitely hope this is worth your time here. So I kind of wanted to start off and make sure that everybody was on the same page as to how trees and stormwater kind of interact, and judging from the list of people and the list of jobs and titles, it seems like most of you all are kind of familiar with the challenges of urban stormwater. But essentially impervious areas are in place and degrading a large amount of our urban waterways and cascading effects to other waterways. And those effects are not just impervious areas, but they're the change in the hydrology overall. We have less trees, less rainfall interception. We have stronger conveyances, so we put in pipes and we put in swales and we try to fast convey water out of the system. So it's not just that we're creating more water, but we're also shipping water out of our system a lot faster. And so there's a number of ways that we've kind of dealt with this situation. And so as we look at the evolution of stormwater management, this is a pretty cool paper by Tim Fletcher at University of Melbourne, and he talks about how we've evolved in stormwater management from simply worried about flood mitigation to over time adding in or rolling in all these other benefits. So now we don't care just about floods, although those are an important consideration, but now we worry about water quality, and we worry about ecology, and we worry about flow regimes. And this is maybe one of the roles and one of the ways that trees kind of fit into to this big picture, right? We have urban heat island mitigation that they provide. They provide green space. They provide the mental health benefits for people. And so part of the reason why we want to study trees and understand their stormwater management benefits is that we know that we get all these other benefits also. And so the more that we can promote them as multifunctional and able to do all these other things, the more we can kind of advocate for their presence in the urban environment. So I think that when we talk about trees, we look at it from multiple different angles. So what is green infrastructure? And to me, green infrastructure is from a holistic standpoint, it's the connectivity of green space across an urban footprint. And so it's forests, it's open space, it's riparian areas, it's parks. And so when I talk about stormwater management and green infrastructure, I'm really just talking about a really small piece of the overall puzzle. And trees are kind of maybe a larger piece of that puzzle in riparian areas, part of urban infrastructure. We've kind of taken for granted what we get from these systems, and so a lot of research recently, and we were just talking earlier about how many papers have come out in the past year or two revolving around the benefits of trees in terms of what they do for urban hydrology. It's very much a thing people are interested in right now. So we kind of have two pieces that we can talk about, and one is their contributions to stormwater practices, and that's some of our earlier work really has related to, if I put a tree inside of a green infrastructure system, what am I going to get from that? Am I going to get, how much ET am I going to get? How much pollutant removal am I going to get? And so our early work with the Forest Service really related to those kinds of benefits. We were really thankful to get one of the National Urban and Community Forestry Advisory Council grants, and our early work was looking at tree function inside of bioretention cells and taking different approaches to that. So using field studies, using full-scale systems, using laboratory studies to really look at what the benefits are. And You'll see on the screen in the middle, the guy in there in the red is my former PhD student, Andrew Turpak, who did a lot of this work, and he's now a postdoc at Ohio State, and he's continuing on his stormwater research up there. So if you see anything from him, it tends to be some quality work. So bioretention cells, we know what they do in terms of bringing back more natural hydrology by promoting evapotranspiration, exfiltration. What we didn't know is really like how healthy are species like trees inside of these systems, and what role does vegetation play. So one of the first things that we wanted to do was a field study and say, we look at all these trees inside of these cells, but are these trees really happy? And what this really goes back to is the way that we select vegetation for things like bioretention cells. And it tends to be, A, relying on what we've used previously for urban trees, which doesn't necessarily mean that that tree will also be good inside of a bioretention cell. We also rely on what's worked in the past, and maybe that is not a bad idea. But the first work was kind of looking through a field survey, and lo and behold, we found some interesting things related to bioretention. Finding out that trees inside of bioretention cells, by and large, are not as happy as their urban counterparts. And so this early work kind of showed us that the type of tree really matters. And when we select trees, we should be really looking for trees that are conducive to the type of environment that a bioretention cell offers, which tends to be harsh, like big changes in soil moisture and big differences in kind of water scarcity at times because we have really sandy soil. It tends to be a really nutrient deficient environment. Other things that we did were looking at greenhouse studies, so trying to look at ET rates of trees inside of urban systems. We did some work on evapotranspiration, kind of looking at what do trees contribute above and beyond just a system that's not vegetated at all. And we found some interesting things, that we can get as much as 10% up to even 50% improvement in ET rates when we put trees inside of our systems. So very interesting in terms of like transpiration, what are trees offering. We also did things just about field studies. So taking things like a silvocell type of system and looking at how they perform, and do they perform the same way as a regular bioretention area? Can we get them to contribute? And by and large, we get really good performance, and so we're looking at about a half an inch of rainfall capture before we see any kind of outflow from the system that we studied. And so we have some papers on all these different things. Andrew's done a great job of kind of documenting his work. If you are interested in any of those, feel free to email me, and we're glad to kind of talk about our work, and so if you're interested in that, just let me know. The other benefits that we have are, so that's kind of what role the trees play inside of our urban green infrastructure systems. Now we really want to focus, and the kind of next group of our research has really looked at, what role do trees play in terms of interception. And, I always tell my students, like, the way we know interception happens is if I'm in the middle of a field and it starts raining, I run to the closest tree, right? And the reason why I do that is I know that there's some protection there, right? I tend to get rained on less if I'm underneath a tree, and that's the easiest way to explain what interception is, right? It's this holding of water that trees provide. And so trees, the canopy in general is the first barrier of defense for gross precipitation. That water tends to get either trapped permanently inside of that canopy, or slowly comes out as throughfall, or it may run along the branches and the trunk of the tree and down as stem flow. And so what we've done is we've not just trapped the water, but we've also slowed it down and I think there's a lot of interesting kind of questions that go along with this in terms of not just interception, but peak flow reduction and elements like that. We worked on a lit review that kind of kicked off this work, and it was with Eric Keeler, and we started looking through the literature on interception. And what you see in literature is that a lot of interception studies historically are based in forested areas. And so I take a big tree canopy and I try to figure out what the interception is. And that tends to be a bunch of different tree canopies that are intermixed, and it's hard to kind of delineate from that what the impact of one singular tree is. And also trees tend to grow differently in things like urban environments. Open-grown trees versus trees grown in more of a forested area. And so we wanted to look at these open-grown trees, and what we found is that there wasn't a ton of information on that in terms of how much water gets captured. Are there specific trees that are better or worse? You can see the list of papers that we see over here. You see some in Australia, you see some in California, British Columbia, and so really kind of specific rainfall trends that are not necessarily present where we are in the southeast. And then you'll also see a lot of things reported as the amount of retention. So how much rainfall retention do we get? It doesn't necessarily tell us on a storm-to-storm basis what kind of performance we get. We've kind of aggregated all our results when we present things that way. So this kind of sent us down this pathway of looking at what do we get from open-grown trees in the southeast. So what's lacking? How do we take those things and equate them to runoff reduction? How do we equate them to scaling those local effects to the watershed? And that's kind of what we're trying to work towards, and a number of other people are working towards across the country right now. So our methodology was to try to take 3 of the common trees that we see around Knoxville, our common urban trees, and that would be red maple, willow oak, and white pine. So we have a mix of our evergreens and or our deciduous and our conifer trees. And so we get different responses there, and we'll talk about it later on. And we're really thankful to the city of Knoxville. They helped us both select our trees and then also allowed us to put kind of some gangly contraptions in their parks, which we appreciate the help of local collaborators like that. So our trees were, in general, you got about a 10-inch DBH, fairly large, from 30 to about 40 feet tall, with fairly good canopy cover, and most of them were in pretty good shape. So you'll see the percent crown missing down there. A couple of them were in the 20 to 25 range, but other ones like the willow oaks and the white pines are really high amounts. So this kind of goes into canopy architecture also. Different types of leaves are different in terms of how they trap and release water. Different trees have different amounts of canopy cover, leaf area index, and all those things kind of play into the overall performance of these tree systems. So here's just an example. This is a dare. This is a red maple that we monitored. You can see leaf on and leaf off, and as you would expect, results are very different depending on the time of year for a species like this. White pine you can see in the background, and then willow oak, and those were kind of those were the 3 that we targeted for. For our study, we tried to find a species that was prevalent enough that we could find 3 of them in one of our parks around here, and also 3 that were kind of conducive to monitoring, which means we can fit all our equipment around it and fit. So as we went into the study, it's kind of interesting, like all the different methodologies that people use to kind of look at interception. And through literature, there's kind of some cool variations that people have done. So you can see in the top left, I had to clip some of these out of articles, and so some of them are a little blurry, but You'll see some people that just take simple manual rain gauges and put them under the canopy like that. Over on the right, this is a little bit of a more complex system, but they had a system of troughs that were built kind of like high up in the tree canopy, so they wouldn't be affected by the understory. And then they actually had another one on top of a roof to kind of use as a comparison. In the bottom left there, this is people have used plastic sheets. So you take a big plastic sheet and put it underneath the tree and funnel the water into an area. So that's some interesting methods, and so we kind of had to figure out, what was the one that best matched us. Stem flow methods are even more kind of tricky, figuring out how to capture water running down a trough. You can see on the left, this is just a tubing that's been cut in half, and they try to funnel water in. You'll see rings sometimes. People will put rings around trees and funnel that water in. It's pretty interesting. So our methodology was to basically take this system of troughs and put them underneath trees. So why do we do that? Well, the difficulty with monitoring interception is that the understory of a tree is very different, and the canopy is very different depending on where you are under the tree. So you have some locations where water may actually get funneled into a specific location. You have some places where maybe there's been some dieback in the crown and you have more water coming through the system. Or maybe you have really good tree or leaf stand on one side and not the other. And so underneath the canopy, there's a ton of variability. If you just stick one rain gauge underneath the tree, you're not necessarily getting kind of an average representation of that system. And so what the troughs allow us to do is go from the drip line all the way into close to the trunk and get a nice cross-section of that system. And what we also did is we did these troughs at 3 points around the understory of the tree. We slope them. Slope in literature and in some of the other studies helps keep the water from splashing back off the pipe. And what we do is we funnel that into a rain gauge, which is fairly consistent with what a lot of other people have done in literature also. So you can see on the left, this is kind of the configuration at one of our sites. You can see the 3 troughs, and they're all dumping into their gauges over there. We used really simple, on-set hobo equipment for our downloads and for our data collection. And every site was basically paired with an open canopy site where we're just looking at raw rainfall amounts. For our stem flow, we had kind of similar to the tubing approach. So we essentially took a tube and we cut it in half, and then we routed that around the tree, and we essentially basically caulk that into place to kind of leave a watertight seal around it and force the water in there. All right. So what we find and what the difficulty is with rain gauges is that there are errors in rain gauges themselves, especially when you do something like we're doing, which is routing more water to the rain gauge than what is supposed to go to a rain gauge. It's something you have to be really careful of. Even a rain gauge just out in the open tends to have some amount of error. I worked on this in my PhD a little bit, and you can get 20% error just having a rain gauge out, depending on the type of rain gauge that you have. So what we wanted to do is basically try to narrow in and calibrate our data a little bit. We went out to all of our sites and essentially had graduated cylinders with different amounts of water that were basically you take an amount of water and you can convert that to basically an equivalent rainfall depth and put that down there over different theoretical depths versus our observed depths, and we can essentially get a calibration line, right? And we can use that information. So for each rain gauge, we essentially had an offset or like a correction factor that we could apply to make sure that our data were kind of where we wanted it, to try to increase the accuracy as much as possible. So we have a large number of storms. We collected data for over a year. over 100 events at each of our for each of the trees that we studied. So we studied 3 red maples, 3 willow oaks, 3 white pines to get a little bit of replication. You can see our range of events from, obviously very small up to a few large events that we were able to capture, and anything from burst thunderstorms down to, multi-day kind of frontal systems that we have in our data set. So this is an example of the type of data that we're collecting. So you see Matthew Howard on the title slide, and he's one of my grad students also, who goes through a lot of this data. So he has had a lot of work and experience going through, think of like 100 times 3 times 3, so, looking at 900 storms like this, basically, and trying to characterize those. So you can see in this, the blue is the rainfall, the red is the throughfall, and you can see how there's a bit of a lag. But one of the things to note is that throughfall is not like it's not a basin, right? It doesn't just get filled up and then overflow. It tends to basically slowly make changes over time, and so it's not like a static storage like we would call it. But you can also see this offset between the lines, and that tells us how much interception we have. So if you were to go from any point on the blue line, go down, straight down, that amount would tell you the amount of basically capture that you have as a result of that system. And then you can also look at things like intensity changes. So for instance, in this case, our peak 5-minute rainfall intensity was 0.6 inches per hour. Our peak 5-minute throughfall was down to 0.4 inches per hour. So we got a decent reduction, 30 to 35% reduction in both rainfall and our intensity by putting in this in. You'll also notice that stem flow tends to be a pretty low amount. So in other studies, you'll see the same thing. You don't tend to get a lot of water going to stem flow, or it's extremely difficult to measure. So, you can take your pick. I think it probably tends to be a low amount of water that goes to that area personally. All right, so what's the other difficulty that we have? The other problem with urban fieldwork is you have a lot of people around, and we have these parks, and some of our trees are located right next to a playground. And I have a kid that's 7, and I have a kid that's almost 3, and the kids at these playgrounds did exactly what I would expect my kids to do, which is take gravel from around the playground and essentially run them down the trough and let them roll down there. And so we had a lot of clogging issues depending on the site. This site in particular was pretty badly getting filled up with rocks from kids putting them in there. We also had some vandalism, so we had a time when people came in and they cut all of our wires, and they kicked around some of our stuff. We'd have leaves drop in there. So there's a lot of kind of stuff that can happen with these open gauges like this, which causes difficulty when you go back and you look at your data, right? And you end up with some of these data points that are off. Exactly, they don't make basically physical sense that you would get the results that you get. And so we wanted to come up with a systematic way of kind of removing those outliers from our system. So what we did was what we find and what we've seen in literature is that we actually get if you just look at the small throughfall versus rainfall events, you tend to get a fairly linear relationship there. So for each rain gauge that we had, we would put a linear regression to it. We would take the 95% confidence bounds around or on either side of that linear regression, and we would essentially move anything or remove samples that weren't within that range. So basically, we took the 5% out of that 95% confidence interval. And it still leaves some events that look a little bit odd. but it's a systematic approach, and that's really what we were looking for. We knew we weren't going to catch everything, but we wanted to come up with kind of a defensible and systematic way to remove those values that seemed a bit odd to us. Okay. So when we start burying into the data, we get some interesting results. And so if we look at, basically if we go over to the right, we look at total interception and stem flow. So what percentage of all the events that we captured went to interception and stem flow. And you can see for red maple and for willow oak, pretty similar, right at about 30%, which is fairly consistent with what we see in literature. Victor ash, which was the white pine, was up to 43, and there are obviously seasonal differences. We get we get seasonal differences in these in the trees also that we'll show in a little bit. Other things that you can see were how much water on average were we able to capture. And so if you look at the average amount across all the events that we have, you're looking at in the range of 0.15 to 0.2 inches of trapping. And that varies dramatically based on the event. I'll show you what those look like in a minute. Stem flow, very, very low on average. So let's look at some of those plots. So this is interception versus stem flow. So these are our gauge data compared to the amount of rainfall that occurred in our open gauges, right? And what we see is we get a fairly linear relationship, but we start getting some tails over here on the right side, and so we do get some limitations. You can see that the different trees are overall stacked on top of each other fairly well. The white pine tends to be a little bit higher on average. This is basically all three of the trees from a given species averaged and put on this chart for a given rainfall amount. So we tend to get a little bit better with the white pine like we saw. The willow oak tends to be a little bit low, and then the red maple is kind of in the middle there. And you can see that you get some fairly high interception stem flow amounts, or water going to those, depending on the amount of rainfall. And so as rainfall amount goes up, we're actually able to kind of sequester a decent amount as things move up. And this is fairly similar to what we've seen in some of our studies and literature also, that again, we don't have a finite storage. We tend to be able to store little bits over in the bark, in the leaves, etc. If we look at that in terms of storm size versus percent interception, you kind of get what you would expect, right? Where essentially the bigger the rain event, the less amount of it you're able to capture. So, 1-inch event, you're going to range from 20 to 60% capture. And one of the things that we want to do in the future, that we're going to dig in the data more and kind of try to explain a bit of this variability. So why do we get 20% in some cases versus 60%? A lot of it plays out with the season. It plays out with the size of the event. It plays out with the duration of the event. All those things tend to change the amount that of runoff that we get, or interception that we get. So we're going to keep kind of digging into these data and try to quantify those things a little bit more. Duration was was kind of an interesting thing, but it makes sense. The larger the duration, the longer you have that water, the poorer our interception was. And those longer duration events tend to produce a lot of water, and so over time you're essentially filling up your interception storage and kind of maximizing what you're going to get there. Other things that we see, I just wanted to show you what stem flow looks like. So while our through fall numbers were fairly high, this is kind of what stem flow looks like. For this one, the bigger the event, the more water goes to stem flow, but in terms of overall water balance, it doesn't tend to be a very big amount. You could argue for some of them, 500ths is not inconsequential, but it tends to be pretty small when you look at the overall picture of things. Obviously, seasonality is one of the most dominant things that we see with trees. Leaf on, leaf off, we get big differences in performance. So what this tells us is this is average percent of interception that we have compared to month. And so willow oak, you can see willow oak in the middle there follows like a very seasonal pattern that we would expect. When you have the leaf off, more in the winter and autumn, for instance, you get lower amounts, right? And same thing with the red maple to some degree. The problem with seasons is that they don't necessarily always follow leaf on and leaf off actual times. So we're going to dig into that a little bit more and look at specifically leaf on and leaf off and make those comparisons. But if you contrast those to white pine, you can see that the white pine obviously has a more consistent performance over time, right? So it's not losing needles over the winter time. We can delve into this a little bit. So this is the red maple again. This shows you the sum of rainfall over here is in blue. So you can see some of the anomalies that happen when we get these smaller amounts of rainfall. We actually had a really rainy event, or rainy, this February. I believe it was February of probably this year. But you can see this is kind of red maple, as you remember in the last slide, didn't seem to show as much of a seasonal pattern as the willow oak. But if you look at red maple in this context, you can see that it pretty much does. You look at December and January, February, we tend to get lower amounts. So kind of some cool things that you start seeing when you start looking at these patterns here. So what are the things that we're trying to do? Well, ultimately, we don't just want to collect this data, but we want to use it for something. And so this is what our group and a few other groups across the country are trying to work on, is like, how do we take data like this and turn it into something useful? One of the things that I think is important to think about is this idea of site scale versus watershed scale. A lot of our stormwater regulations are based on site scale management. So I'm getting credit for what I do specifically on this site scale. Some of the benefits from things like trees are really probably seen more at the watershed scale, where I'm making a big effort. Let's say I'm a municipality. I'm not looking at a parcel, for instance, but I'm looking across an entire watershed, and I'm trying to look at implementing strategies like trees. And it's probably more effective when you think about it on that basis. Like I said earlier, trees have a lot of benefits. And so when we try to quantify things like stormwater management, it's kind of one tool that we can use to promote tree presence. It's hard to, some of the soft benefits like aesthetics and green space and things like that are harder to quantify in terms of like monetary benefits, but we can easily sell the stormwater benefits and kind of try to promote trees by giving us something that we know we need, and in reality we're getting all these additional benefits too. So what contribution do they make to peak flow reduction, to volume reduction? All these things are kind of the places where we're trying to drill this data and kind of understand how it plays into these bigger systems. And really what we're trying to do is the stormwater industry works a lot of times on this idea of credit. So whether you're in Chesapeake Bay and you're worried about nutrient credit, or you live in a municipality that uses the runoff reduction method, you're trying to assign numbers to things. If I put in a tree, what percent of my 1-inch storm am I able to take care of, or can I get credit for some amount? And so there are some efforts that are ongoing across the U.S., and I wanted to point out a few of those things. I saw Bill Selvig is on the line, and they're doing some really great work up in Wisconsin to try to look at some of these same things of how do we get these turn results like this into usable information, and can we collect the type of information that we want. So Chesapeake Bay has put together an expert panel, and one of the things that they were trying to look at was urban tree canopy. Can we get basically BMP effectiveness, or can we call that a BMP when we expand? And you can see the name of people that took part in that. Some very good researchers and experienced people in this field of how to take numbers like this and generate guidance from that. So I would kind of point you towards things like that as a way to kind of understand how how people in other places are dealing with this crediting system. Other things are Center for Watershed Protection. It has a kind of a complementary piece to that work. They have an initiative called Making Urban Trees Count, where they've come up with a model, and they're trying to look at some of these things like, if I have an individual tree or a certain project design, how much credit should I get for that? And so both of these efforts are they look at runoff reduction, but they're also looking at nutrient removal. Like, can we take that runoff reduction and equate that to some kind of nutrient removal? So there's a website that they have together, Making Urban Trees Count. They have a bunch of documents that they've put together that are really kind of relevant to this topic also, that could be useful. The other thing, and the last one that I wanted to talk about, was Kansas State University. There's a researcher there, Tricia Moore, who's on faculty, and she's been funded by WRF to do basically a big lit review and assessment of these kind of data. And so she's been scouring data or scouring studies and looking at that data that fall into this category, and trying to make some sense of it, develop some like applicable models that can be used. So what I think we're working towards is, I think the first crack at giving credit has been trying to take this data from a bulk sense, take all these different studies and figure out, on average, what's the removal that we should be giving to people. But I think what we move towards more and more is trying to model that and really get down to specifics. One of the issues that they run into with studies like this, and that they bring out in this the Urban Tree Canopy Expansion Expert Panel, is that how much removal you get depends on a lot of things. And it depends on leaf area index, and it depends on the type of tree and the type of storm. And there's a lot of variables that go into that. So while I think the initial kind of assessment has been, let's put some blanket numbers down there, I think what people will begin moving toward is being a little bit more specific with that, where, if you have a tree and you expect it to have this leaf area index, this is what you can expect to get. So I think we're going to narrow in on specifics a little bit more. So the study by Kansas State, Tricia Moore, should be coming out here fairly soon, and I think that'll be a really great kind of summary of a lot of this stuff. I know her, and she does a fantastic job with these types of studies. So as part of our work, I'd like to thank Eric. We've worked with him for, I'm guessing, 5 years or so, and the Forest Service. It's been a great experience, and hopefully we've put together some data that's usable for people. Casey Krause is with the city of Knoxville. He helps us a lot with finding sites, giving us permission, making sure we're not doing anything stupid to the trees, et cetera, which is good when you have a bunch of engineers running around trying to collect data. And obviously the Forest Service, who's funded so much of our work here. So I think we're going to do one thing before we do questions, but This is my website's hathaway.utk.edu. My email is just hathaway@utk.edu, and if you have things that don't get answered here, or you want some of those other resources, or you want to see any of the studies we've done previously, you can feel free to email me.